investigating this compound to elucidate basically the crystallization of this API using the classical nucleation theory, and see how the solvent choice impacts the crystallization of this API, and perhaps to come to a better form. So for the classical nucleation theory, one way to use this theory is to use induction times. So induction time means that you have crystallization at a fixed supersaturation and a fixed temperature. And if you apply these conditions, then the time depends on when you have crystallization, and that's called induction time. So what you do is you have clear solution, for instance, an HPLC file. You make it slightly supersaturated by cooling. You have a laser, and then if you have a detector as well, you will see that the transmittance is about 100% because it just goes through. Then you wait, and at some point you have primary nucleation. Usually this is not immediately detected, but usually nucleation also triggers secondary nucleation. The file rapidly becomes a cloudy suspension. And in this case, the cloudy suspension will block the laser light, and the transmittance will go down below 100%. And that's when you know, okay, we have crystallization. And since nucleation this way, crystallization is is a stochastic process, you need to have many induction times to use it in the classical nucleation theory. So we collected those those induction times with Crystal16. Graphically, it looks something like this. So we have on the horizontal scale the time in hours. On the left-hand side in blue, temperature, and the transmissivity, so the amount of laser light that's passed through the vial, isn't shown in green. So typically you would heat up until everything dissolves, cool down until you have a saturated solution, a supersaturated solution, I should say. And then you wait until crystallization occurs. And here you can see crystallization occurs quite rapidly in the beginning. And in the second experiment here at 5 hours, you see also again crystallization occurs quite rapidly. Here around 20 hours, you see that a slightly longer crystallization time is needed, but you see that that a lot of time is actually lost, because once you know the induction time, you can actually move on to the next experiment. So what we used in our experiments is a feedback loop, also part of the Crystal16, where we started the next experiment when the transmissivity was below 90%, so when crystals were present. And that way we could actually significantly reduce the experimentation time. And that way we could do a lot of experiments in a small amount of time. For our work, we performed in total more than 1,800 crystallization experiments within a month. And we tested 5 solvent systems, and that way we could obtain 50 to 160 induction times per supersaturation per solvent. So if you have all that data, typically what you would do is rearrange them into a probability figure shown here. So here you see the probability of crystallization as a function of crystallization time or induction time. And the different colors denote different supersaturations. So the red color is a low supersaturation, and the orange color is the highest tested supersaturation ratio. And in this case, water was used as the solvent. So at the low supersaturation, you see that after 15,000 seconds, about 50% of all vials have crystallized. But if you look at the other supersaturations, if you go slightly higher, then you see that the chance of finding crystallization at a high supersaturation becomes 100%. What's interesting here is that in water, we noticed in combination with pregabalin that a small supersaturation was needed to already induce nucleation, but also the range of supersaturation was quite narrow. Because if we looked at another solvent system that we tested, namely methanol, we noticed that a much higher supersaturation ratio was needed for crystallization, and also the range of supersaturation was much wider. So already at this stage, we noticed, okay, there is something going on with the solvent choice. So once you have all this data, you can actually fit it to this formula, which shows the probability as a function of the nucleation rate, J, the volume of your reactor, V, as a constant, T is the induction time, and the Tg is the growth time of a nucleus. And the nucleation rate and the growth time you can get basically from fitting this equation to the data. So in the graphs, you see the line that's actually the fit from the data. And also, if you want to know more about this approach, there's also a webinar from Joop de Horst, also on the Technobiz website, that explains this